A very good morning to everyone. Myself Pujita. As today I am here to give a presentation on control systems. My topic is state transition matrix problems. So in these problems, here having introduction, procedure, conclusion and then result. So introduction to state transition matrices. State transition matrices are mathematical tools used to describe the behavior of dynamic systems over time. They represent the probabilities of transitioning from one state to another in a state space. Applications include fields such as engineering, economics, and biology, where system evaluation is analyzed. Procedure for analyzing state transition matrices. The first step involves defining the states of the system and constructing the state transition matrix. Next, calculate the transition probabilities, ensuring that each row sum of 1 to maintain proper probability distribution. Finally, use matrix operations such as multiplication to predict future states based on the current state vector. Example problem and solution. Consider a simple Markov process with the three states A, B, and C defined by a specific transition matrix. By applying the transition matrix to an initial state vector, we can compute the probabilities of being in each state after several transitions. This example illustrates how the state transition matrix can effectively model the system's behavior over time. So it is the problem. For example problem, compute the state transition matrix for given A. A value is given matrix A equals to 1 0 1 1, and by using this formula, that is phi of t equals to L inverse of Si minus A inverse. In this Si minus A inverse, we had to change that Si means S should be right in a I matrix, that is S00S. Si, it is Si, and A is 1 0 1 1, it is the A. So Si minus A, by multiplying the Si and minus into A, we get S minus 1 minus 1 0 and S minus 1. Si minus A inverse, we had to compute that by using the formula 1 by AD minus BC into D minus B minus C and minus A, 1 by S square minus 2S plus 1 into minus 0 into S minus 1, 1 0 S minus 1. By getting this S square minus 2S plus 1, that is, we are find out in the roots, it is the root value. How to we are find out that roots is by finding the roots, that is S minus 1 into S minus 1. By multiplying these two factors, we get S square minus S minus S plus 1. S square minus S is equals to minus 2S plus 1. We getting the roots that 1 comma 1. Si minus A inverse equals to 1 by S square minus 2S plus 1 minus 0 into S minus 1 1 0 S minus 1. Si minus A inverse equals to S minus 1 by S minus 1 into S minus 1 and 1 by S minus 1 whole square 0 S minus 1 by S minus 1 into S minus 1. Here same values should be cancelled. In this first step S minus 1 should be cancelled, and here next of this 0, the both numerator and denominator of S minus should be cancelled. Then we get, it is the formula. By using this formula, we get the value of state transition matrix. Solution: 1 by S minus A whole power n equals to e power at into t into n minus 1 by n minus 1 factorial. By using this formula, we get the value of the solution of the state transition matrix. Si minus A whole inverse equals to, in before slide we cancel that numerator and denominator same factors, that is S minus 1, that we get 1 by S minus 1, 1 by S minus 1 whole square 0 and 1 by S minus 1. By applying the inverse Laplace transforms, we get the solution or value for the state transition matrix, that is, it is the final value of state transition matrix. By applying the Laplace transforms, we get L inverse into Si minus A whole inverse equals to e power t, t into e power t, 0 and e power t. It is the final solution of the state transition matrix problem. Conclusion and result. State transition matrices provide a powerful framework for analyzing dynamic systems and predicting future states. The results from our example demonstrate the utility of these matrices in revealing long-term behavior and trends. Understanding and applying state transition matrices can significantly enhance decision making in various fields by providing clarity about system evolution. Thank you.